Finding lengths, areas, and volumes might seem like nothing much in class, but you're learning the language of the universe. Have you heard of sacred geometry, or ever wondered why so much religious symbolism uses the shapes that you've learned equations for in maths class? Have you ever thought about why a circle is the way it is, or what the different branches of geometry are all about? We're going to talk about that and so much more, and sort of scratch the surface of the magic in the discipline of earth measure and why it's such a beautiful part of mathematics. But of course, before we get started, everyone, welcome back to GCSE Minecraft and Chill, the series where I chat about something relevant to your GCSE maths and science exams, or play Minecraft to entertain myself and maybe you. I hope your evening so far is cozy and warm and that you've got a drink and something to do while I talk about geometry. I have been, not gonna lie, really excited for this video because geometry is everything. Geometry is about measuring stuff in real life, or at least that's how it began. And we can measure abstract things and develop branches of geometry that go way beyond everyday life. But primarily it was about measuring stuff, right? Like circles, squares, lines, angles, triangles, all the good basic shapes that we know that make up most of the stuff that we see and give us clues about the nature of things that we can't see, both microscopically and more broadly out into the universe or even beyond into the spiritual realm of reality. And I appreciate geometry because, like certain parts of calculus, which I also loved as soon as I learned how to differentiate from first principles, but that's a whole other video. What I loved is the elegance of it all, which is a word that I use all the time to describe maths whenever I'm talking about it, because it just is. And I appreciate that if you complimented someone by saying that they're as elegant as a hybrid exponential and trigonometric differentiation equation, they probably feel insulted, but they would be wrong. They shouldn't be insulted. It is elegant. There's no way around it. It's simple and yet it also clearly isn't, and it takes people in, in the standard education system years to build up the skills required to understand and appreciate the concepts. So they're simple but deceptively simple, right? And geometry is like that. The longer you study it, the deeper your appreciation can become for the things that appeared at first glance to be simple. And I also love that geometry reveals to us the nature of space. And I don't mean like space like stars and galaxies, I mean literal physical space, 3 dimensions, 2 dimensions, also however many dimensions we want. We can do geometry in whatever number of dimensions. The rules and logic of geometry reveal relationships within space and the aspects and nature of certain defined shapes, regardless of whether that's because we decided to define the rules of geometry that way, or because we humans are just simply discovering a quantitative aspect of our shared reality in matter and space. And that fascinates me. I'm gonna try to explain what I mean by that. So, numbers are sort of an invention of humanity, right? Like, we decided to label quantities of things. Quantities aren't an invention, they are just a material consequence of having a separation of matter that forms lumps and clusters that we recognize as separate, right? Like the orange is separate from the tree. But that, that's a natural phenomenon that there's a separation, but the molecules within those things, where we can count them, we can count how many apples you have and how many bananas your friend has. So it is a natural phenomenon to have quantities of things, but we label them with the numbers that we have and the rules that we have around how those numbers work. But when we investigate them, because they are a consequence of something natural, we're kind of discovering the properties of number, right? Well, sort of and not really. It's kind of a grey area, a both, a yes and a no sort of. We decide to apply certain rules and logic to things, and that leads to different systems of number and the realm of logic that governs how we apply operations and calculations and everything. But there are certain kinds of things that have a natural logic or natural consequence to them. So take, for example, counting in twos. So only multiples of 2 have the property of evenness, which doesn't really mean anything or matter for anything in particular if you're just looking at what evenness is on its own. But it does reveal something about the nature of our counting system, that we decided we had this property and we labeled and called it evenness, and that means that it's divisible by 2. Or you can share it into equal parts or that are, evenly symmetrical or whatever. Oddness then becomes the opposing trait, where that previous thing isn't true. That's inherent to how counting works. We have odd numbers and even numbers. That's just how quantities work. But you can see also how, while we kind of discovered these natural properties, they are still ultimately just labels that we have pinned to things that we decided to notice because it was useful for some reason or another, because it seemed like an obvious natural trait of the system that we were defining. So it's kind of like a consequence of both the logical definition and defining points that we need in our counting system to understand the quantity and shape of things, but also once we define those things, a sort of natural logic seems to be discoverable about it, right? So if that made absolutely any sense at all, apply the same reasoning to geometry. We decided that a circle, just like evenness, was just the label that we were going to give to the specific shape whose circumference remains at a constant equal distance away from the center of the shape for a full rotation. That's a circle. But then because of that property that we have defined or noticed about this shape, hundreds of other things end up being true. Just like how evenness spirals out into so many other consequences of adding, multiplying, dividing, powers, multiples, and factors, and so on. Is that not magical to you? Maybe it's just me, but to draw a fully internally consistent system of logic and laws and rules that prove themselves, that consequently prove other things, that help us understand the nature of the space and matter that we exist within and are comprised of, distilling some like chaotic, non-linear jumble of cascading probabilities, fixing that initial condition, whether that's counting up in whole number ones or whether defining a circle as a circumference being a fixed distance from the center for a whole rotation, and then suddenly order manifests. The equations have solutions. Linearity and logical consequences without instability are possible. The universe suddenly seems to have some design and architecture to it that makes sense. Pretty much all of science is sort of loosely based on that principle, and why I think so many people find intelligent design to be such a compelling theory, when really it's just because we humans a long time ago, in the birthplace of all humanity in Africa, decided to invent a system of consistent logic by saying, what if? And then fixing that initial condition that defined this thought experiment. And then suddenly so many other things could be discovered, properties could be eked out from the jumble of observations that seem to have no pattern or form, until someone notices and connects the dots and sees that pattern emerge, and then that can be applied ad infinitum to so many problems. And that all helps us understand how other systems function and integrate with one another. That's kind of the power of geometry. And that comes from the principle that we decided it was a good idea to start counting things. So I've mentioned a few times, and I've kind of hinted at it, but geometry is connected to literally all religions on Earth too. So while the phrase sacred geometry, if you have heard it, you've probably heard it aligned with, utilized by, or associated with New Age spirituality movements and communities, every established major religion on Earth has imagery and association of the divine that uses geometry as the fundamental symbology for that divinity. And while that sounded like a little bit of a word salad, what I mean is that there are building blocks of geometry that you'll recognize that have historically conveyed or meant or symbolically, had the attributes of divinity and the divine structure, nature, or symbology of the universe itself. One of the examples of this is the 5 Platonic solids, and the images and the symbols that arise from them, like classic examples of the seed of life, the tree of life, the tetragrammaton, or Metatrons, cube, yantras, as well as things like symbols like the yin yang symbol or the Star of David, things like that. So the 5 Platonic solids are 3D structures comprised of regular polygons to create regular polyhedra. And by that I just mean shapes and a fancy word for a 3D solid shape. So for a regular polyhedron, the faces have to be the same size and shape. They all have to have equal sides and equal angles that meet each other at the corners or a vertex or vertices. And these 5 solids, the tetrahedron, the hexahedron, also known as a cube, the octahedron, the icosahedron, and the dodecahedron, they each have spiritually symbolic meanings attached to them, and they are the 5 elements of fire, earth, air, water, and ether, or spirit, respectively. And they each come from triangles, squares, and the pentagon. And they are thought to be the divine, fundamental building blocks of our world. And that's sort of true. We see them in crystal structures, in geology, molecules, in chemistry, in all sorts of natural biological formations in biology, and in space, light, and sound phenomena in physics. So while the ancients understood this differently, obviously they didn't have the same evidence that we do for those things today, they still made incredibly accurate geometric observations and intuitions, and they were societally and culturally and religiously fascinated with these shapes and described them as the language through which to understand the portal between our material world and the divine spiritual world of energy that exists all around us. And this incredible appearance of a material order in a universe of chaos and infinite possibility inspires humankind to imagine or reflect a greater spiritual metaphor or divine truth revealed by these geometric structures that have given us the secrets along the path of spiritual enlightenment. But, before I sound like I'm proselytizing, let's ground ourselves and talk a bit, perhaps more usefully for you and your GCSEs, about what geometry involves and why you have to know it, rather than why I personally think it's cool and why cultures and societies all over the world have found geometry to be pretty cool for a long time. So, let's get into it. Geometry, like I already said, is about measuring stuff in space. So that means defining shapes, spatial relationships, their properties, especially if that relates to real life problems. Like early examples of where geometry was used was, what is the circumference of the Earth? How far away is that star? What is the best shape to support a large building? How do I faithfully reproduce this view in a painting? And so on and so on. And this is empirical, practical, Euclidean geometry, and usually relates to finding lengths, areas, and volumes, things like that. But like I said, there's a lot of different branches of geometry, and they've all got multiple names, and it can get really confusing. And in recent history, we've taken to naming them after whichever man happened to write about them in a certain period of history, regardless of whether that individual man happened to invent or discover it or whatever. And they usually just compiled or translated an earlier work of the same thing. But anyway, um, that's what Euclid is all about, and the type of geometry I was talking about before. He wrote a book of these geometric principles, and it's actually a really solid foundation for understanding geometry, and it's included in the list of resources below, as you can read the PDF of someone very helpfully translated Euclid's elements, and digitized it and gave it diagrams and everything, so you can read that as a PDF online for free. But also, equally, you might have heard of non-Euclidean geometry and wondered, what is that all about? This covers the world of geometry that sort of breaks the rules, or sort of more aptly bends them, I suppose, of the traditional Euclidean geometry by considering deformed frames of reference, or 3D and higher dimensional spaces and rotations, strange curves, especially as it relates to parallel lines. So you might have heard of hyperbolic, spherical, elliptical, or other types of geometries that all involve curves, curved planes, curved surfaces, and the strange consequences that sort of enacts on right angles and parallel lines. I'm actually going to link a really fun, very trippy video that kind of demonstrates this in a digital simulation in the resources list as well. So do check that out. And there's also things like analytical geometry, which is about relating coordinates, differential geometry relating to calculus and curved surfaces, and other branches of geometry which are far more complex, like topology. See the encyclopedia entry I've linked below in that list for a short summary of all the different types, because we do not have time to get into it all today. But what you learn first at GCSE is just some good old-fashioned, simple Euclidean, plane geometry, solid geometry, and a little bit of coordinate geometry. You also begin to learn how to form accurate constructions with just a pencil, a ruler, and a pair of compasses, which I find really fun. It's cool to be able to, just with those simple tools, construct any shape accurately. with accurate angles. I think that's cool, but anyway. How to find lengths, areas, volumes, like I said, and angles in basic shapes, regular polygons, and things like cubes, cuboids, prisms, spheres, cylinders, and cones. So you learn how to do all of that, you learn the basics of all of those shapes and how to calculate their sort of basic properties. You might also learn about 3D projection, so nets, different 3D views like plane view, front view, um, all very important things for understanding perspective in art and animation and other kinds of creative visual media, as well as for engineering and science, of course. And then the sort of the more complicated, I think, topic is angles, trigonometry, things like the Pythagorean theorem, all important for those of you wanting to become engineers, designers, architects, or scientists. Uh, but really, the usefulness of trigonometry cannot be understated. I actually love triangles. Well, all the regular polygons are really cool. They're just satisfying. But triangles are the first example of geometry that I think a student will come across where you can appreciate just how many rules and consequences and logical proofs can be abstracted and deduced from such a simple concept of three lines stuck together. And that's kind of even more so true with the circle. When you combine circles with squares or quadrilaterals or circles or triangles, suddenly the amount of things you can prove are mind blowing, right? Like, is that not mind blowing that just from constructing a few lines, you suddenly get all of these logical, provable properties? Maybe not, maybe it's just me, like I said, but I do personally love it. And I wish that there was enough time in the modern curriculum for you to really explore all of these cool and interesting consequences of geometry and their applications. Like, for example, why triangular nets simplify the programming required for a computer to more faithfully reproduce an irregular curved surface, like in a video game, as opposed to using smooth curves or quadrilaterals. Like, why is that true? I didn't learn about that until I was at university, and it was just randomly during a geophysics course. Really strange place to be learning that. Scientists just happen to be weird and full of random knowledge from all over the place, which, in my opinion, is what makes us great. My not so humble opinion, perhaps. Um, but speaking of random teachers and Pythagorean maths and triangles, um, I would be remiss if I didn't mention my GCSE maths teacher and the trippy video. And I actually think I talked about this possibly in the first or second maths video in this GCSE Minecraft and Chill series. Because I don't know, it was just so strange. Like it got stuck in my brain. So when I was at school, my maths teacher put on this video during class of it's called Donald Duck in Mathemagic Land, and it was such a strange, cute, trippy video that just made maths that day just seem a little bit more interesting. And watching it now just gives me so much joy. Stuff like that really influenced me because I didn't enjoy maths very much at school, but it made it seem genuinely so much more magical and like rewarding to learn about than a textbook would ever tell you. The video shows some examples, starting with music, of how maths is just everywhere in life, and some of the things that the Pythagorean secret society discussed and learned about, and how that has influenced a lot of the maths that we talk about today. And I could do a whole video on the Pythagoreans, or what influenced them, and how their symbology has influenced modern conspiracy theories, modern spiritual communities, and maths and science in general. Because understandably, the Donald Duck in Mathemagic Land video, being only 27 minutes long and designed for young people and kids, doesn't really get into the thick of it. And I think it would actually be quite cool to do a video on them. So let me know if you want me to do a video so you can learn more about those guys, because they are cool and interesting. But anyway, one of the things said right at the end of that video that sticks with me to this day is how all human knowledge is like a chain made up of chain links of one piece of mathematical or scientific knowledge, all connected to one another infinitely. And learning to trace back the chain and appreciate what was understood before so that we can continue to reforge or forge new links is why I value education and teaching so much. New branches of science and maths are still being created, and connections between disciplines are being forged all the time. There are still so many questions that don't have answers, let alone questions we haven't even begun to ask yet. And the video visually represents this as a series of open doors in a corridor with answers beyond them, or discoveries, or the fruits of the labor of such discoveries. And yet there are infinite doors of the future that aren't open yet. And it's going to be the job of future generations, possibly you listening to this video, to figure out what key unlocks each door with the knowledge of the doors that were open before you. And I I hope that I don't know, is that not inspiring? I find that quite inspiring, especially as someone about to, or nearing the end of my PhD thesis, where I have literally just opened a little door, my own personal little contribution to knowledge, and that's really cool. I don't know. Um, I hope that small dip into the pool of geometry of geometric knowledge entertained or inspired or helped you revise some concepts a little bit, or even if I was just background noise while you did some practice questions. Either way, geometry and its principles are a fantastic tool to have on your belt, probably regardless of what you end up doing in life, and yet there are so many uses and applications of it that we haven't even conceived of yet, and that's pretty exciting. So I'm going to leave you, as usual, with the reminder that while maths is magic, your words are spells. So always be kind to yourself, be conscious of others, and have a lovely rest of your week. Thank you for being understanding while I'm reducing my video output for the time being, but I will see you next week. Yalla bye.